get started, the first thing on the list, are you able to take that to the other side so they can see? Okay, yeah, so the first thing on the worksheet we have is assigning oxidation numbers. And there's a couple of rules for oxidation numbers. Do y'all remember the rules here? Let's start with the first element on the periodic table, hydrogen. Do you remember the rules for hydrogen?
+1 when it's paired up with a non-metal, and then negative is the other way around.
Yeah,
So it's so
no, it's +1 when it's with the non-metal, yeah, and then negative when it's.
yeah, so hydrogen is a
Yeah, sorry, I was just processing.
Plus
Like,
one.
I was processing what you said.
when paired up with, when bonded to non-metal, or you can say when it's in a covalent compound. Hydrogen is -1 when bonded to, or when in an ionic compound. Okay, so an example of each one would be methane, or so for the first one, a good example is methane, so CH4. In this case, each hydrogen has a +1 charge. And the carbon would have, in order to make this neutral, so that it has an overall charge of 0, what must the carbon have? -4, right? So each hydrogen has a +1 charge. The carbon, in order to make this 0, must have a -4 charge. Okay. Now, for the other example, let's do something basic like sodium hydride. We know sodium is a metal, therefore the hydrogen is going to have a -1 charge in this compound, in this ionic compound. So we end up with sodium having a +1 charge and hydride, or the hydrogen in this one, having a -1 charge, right? So then when you do your crisscross, if you were to do the crisscross, you would get sodium hydride, right? Now, what's our rules for fluorine? Always -1. And why? We're going to learn that fluorine is the most electronegative atom. Eventually we'll learn that. So it's always going to want to take electrons from other elements. It's not going to want to donate any electrons. So it's always a -1. What about oxygen? So 99% of the time, oxygen is -2. Is there another time when oxygen has a different charge?
When it's paired up with fluorine, it needs some positive charge, isn't it? Because
Yeah, so
Yeah.
oxygen, when it's bonded to fluorine, we said fluorine is always -1, right? So when you have something, like we'll see later, when it's bonded to fluorine, it's gonna have a +2 charge.
There's one more case where oxygen isn't -2. Y'all know what it is? Peroxide, yeah.
And then we have oxygen, again, when it's the peroxide anion, so O2, 2-. Oxygen, each oxygen is gonna have a -1 charge, right? Because you have an overall charge of 2, a -2, right? But you have 2 oxygens, so they're splitting the charge equally, so each one has a -1 charge. -1 oxidation number. Okay, now with those rules, we should be able to answer the rest of the questions, okay?
So these are the only rules for oxidation.
Yeah. So the first one, oxygen difluoride. We know just from previous exams, we know how to go from the name to the formula, right? So I'm not going to go over that. So oxygen difluoride is OF2. What is the oxidation number for fluorine? -1, right? And that tells, and what do we know about oxygen when it's bonded to fluorine? It's +2, right? Because fluorine's going to want to pull on those electrons as hard as it can, giving oxygen a +2 charge in this case. And this is the only time you'll see oxygen with a positive oxidation number, okay? What about for ionic compounds like calcium hydroxide? I like to split it up, right? So we know we do the reverse crisscross, we do calcium has a 2+, and then OH minus has a -1, right? So it already gives us what it is for calcium. We know calcium has a +2 oxidation number. But for hydroxide, it tells us that the overall charge is -1. And we know oxygen is going to be -2, right? Because it's not any of the exceptions. It's not peroxide and it's not bonded to fluorine. So it's -2. And that tells us that the hydrogen must be +1. And when you add these together, -2 + 1 equals -1. So you still remain with your overall negative charge, which is why hydroxide is an anion, right? It has that overall negative charge. Does that make sense?
Yeah, the hydrogen is -1 because it's in.
So remember, this hydrogen is only a -1 when it's directly bonded to a metal. So like we said up here, when you have sodium hydride, you have sodium and then the hydride with the -1, right? In this case, you have a calcium bonded to a hydroxide. And when you break it up, you have your hydroxide ion, which has an O bonded to an H. So the H is not directly bonded to the calcium. Does that make sense?
Yes.
Okay. Now, if it was, like we said before, sodium hydride, that H is directly bonded to the metal, so therefore it has a -1 charge. Does that make sense?
Yeah, thank you.
All right, so we already said calcium has a +2, oxygen has a -2, and then the hydrogen has a +1. Okay. What about S8? 0. Okay, so we know that elements in their natural state have an oxidation number of 0. So natural state,
It's alone.
yeah, alone, or in this case, you have an octaatomic, sulfur is octaatomic, it naturally occurs as S8, right? So it's gonna have a oxidation number of 0. Another example would be calcium solid. Just pure calcium metal has an oxidation number of 0. Oxygen gas, O2, naturally occurs. Oxygen is naturally found as O2 gas. Therefore, this has an oxidation number of 0 as well. Those are just a couple of examples. So anything in their natural state is going to have an oxidation number of 0. You're welcome. Zinc permanganate. So what is zinc permanganate? We already know how to write the formula, right? So it's ZnMnO4 2. We know how to do that from everything else we've learned. But what's easier when you're assigning oxidation numbers for ionic compounds is to split it up into their cation and anion. So if we do the reverse crisscross, we know that zinc is 2+. So that automatically tells us the oxidation number for zinc. And then we know MnO4 permanganate always has a -1 charge, right? So, but that -1 charge is for the overall polyatomic anion. So let's go for each element in permanganate. We know oxygen is what? -2, because it's not bonded to fluorine or it's not peroxide, right? So it's -2 for sure. So let me go ahead and move this over so we can have some space. So each oxygen has a -2 charge. And we have how many oxygens? 4, right? So I'm going to multiply this by 4. And we know that the overall charge is -1, right? Because permanganate has a MnO4 minus. That minus tells us that the overall charge of this is -1. Does that make sense?
Yeah.
So I'm going to set this equal to -1. And we have 1 manganese in here. So I'm going to do that in blue. And we don't know what the charge on manganese is, but we do know that, so we're going to put it as X, but we do know that the sum of this has to equal -1. So if we just do basic algebra, we can say X plus, if we multiply the -2 times 4, we get -8. Now I'm just going to change this to that. So X minus 8 equals -7 or -1, my bad. So when we solve for X, we add 8 to both sides. plus 8, and we get something down here. We say x is equal to plus 7, right? That's just the algebraic way of finding what manganese is. All right, so does anyone want me to repeat how I got that?
You put the 8 to eliminate the minus and the 8, right?
Yeah, so what we said was we have 4 oxygens, right? Each one has a -2 charge. We need to find the charge on manganese, the oxidation number. And we know that the total charge of this polyatomic anion is -1. We get that from this little minus sign here, right? It tells us that there's an overall charge of -1, right? So we know that all these charges in here have to add up to -1, right? So we say each oxygen has a -2 charge. We have 4 of them, plus the charge on manganese, which is we denote X equals -1, right? Does that make sense so far? And then we just solve it algebraically. So we get, when we multiply the -2 times 4, we get X minus 8 equals -1. And then we just add 8 we add 8 to both sides and we get X equals 7. Does that make sense? Okay. Sure. So that tells us manganese has an oxidation number of +7. Each oxygen has an oxidation number of -2. Okay. What about MnO7? I'll let y'all try this. Give you like 30 seconds, see how far you get. See if you can solve it. All right, so is it okay if I pick on you, since I know this is the stuff that you said you're having a little bit of a hard time?
Fine, but I didn't, well, I don't know if I'd solve it.
All right, so what is the overall charge on MnO7?
I didn't get to that, but I was like doing -2 for oxygen. And I was putting the algebra thing that you
Yeah.
just do, like -2 plus 7 multiplied by 7.
Well, only if, so let me show you how I would do it, okay? So let me ask you, do you know what the overall charge is on this MnO7, on this compound? All right, so we said before that we know that the overall charge on MnO4 minus is -1 because there's a -1 right here, right? Do you see any numbers up there that tell you? So that tells us that their overall charge is 0. Okay. Because it's neutral. Now, if it had plus or minus, then it would be a -1 charge or +1 charge, okay? So the fact that there's no charge tells us that this is 0, right? We know that we have a total of 7 oxygens, right? Each oxygen has a charge of what? Oxidation number of what? -2, right? -2. And we have how many manganese? We have 2 manganese. And we don't know the charge on manganese yet. But we do know that we have, so we're just going to denote that X, okay? And we know that the overall charge has to equal what again? 0, right? Because it tells us, or it shows us there's no charge here, therefore the overall charge has to equal 0. So let's multiply this out. You get 2x plus 7 times -2 is -14. So -14 equals 0. If we want to isolate x, what we'll do first is add 14 to both sides to get 2x is equal to 14. Then we're going to divide by 2 on both sides to isolate x, and we get x is equal to 7. So in this case, the charge on manganese is still +7, but we found out from doing our little algebraic expression. So does that make sense?
Yes.
How about you walk me through this one more time? You tell me all the steps that I took.
Okay, first you look at the charge of the compound.
Uh-huh.
And then you put all the information that you have in an equation.
Uh-huh.
And you solve it
And you
like
said it equal to the what?
to zero to the general charge.
To the charge, right? Yeah.
And then you solve it like math.
Yeah, just using the math that we know that we learned, right? And we get our charge on manganese is 7. So here we have, our answer would be +7 and -2 for each element. All right, what about, you're welcome. How about, go ahead and walk me through this one. What's the overall charge on this?
It's the same zero.
0, right? So we can just put a little 0 right there. That's the charge. So we have how many oxygens? 4. And each one has a charge of what?
-2.
And -2 because it's not bonded to fluorine, and it's not peroxide, right? So -2.
Peroxide is when you have the -2.
Yeah, so peroxide is O2 2-. Right, but we're not dealing with that in this compound, so I'm gonna erase that. And we know that we have one, how many osmiums do we have? 1, right? So we're just gonna put 1x, okay? And this is equal to the overall charge, which is what?
0.
0, right? So when we solve for x, we get x -8 equals 0. If we solve for x, we get x equals 8. We add 8 to both sides, right? Does that make sense?
Yes, thank you.
Yeah. Okay. So again, each oxygen has a formal charge of -2. The osmium has a formal charge of, or not a formal charge, an oxidation number of +8. Okay.
I have a question, just a mathematical question. You put when you want to change the charge or you put the same number in both places, like to eliminate, but you don't multiply and you don't do nothing, right?
When you, in what, did we do something like that? So I
Yeah,
can
with
see,
the 8 and the 14.
oh, right here.
Yeah.
So where do we get the 4? Right here,
Well, in the it's fine.
right?
In the one that we solved,
This one, this one,
yeah, this one, you put them x -8 equals 0,
correct.
and to change to, you just,
To solve for x.
yes,
Yeah, so because it's x -8 equals 0, to solve for x, we have to add 8 to both sides. Right? Because if we add 8 to both sides, you get x -8 plus 8, which is cancels out.
Yeah.
And then you add this 0 plus 8 is equal to the 8 that we're getting in the oxidation number, right?
yes, perfect, thank you.
Okay, I'm gonna jump down to, you can do number or letter G and H on your own time. I'll do at the end if we still have time, but I want to go ahead and get to the next type of problem. So let's do this last one, I. We know plumbic is lead with the higher charge, which is what? +4, right? So lead +4. And then chlorate is, do we know what chlorate is? Is that perchlorate?
CO3.
Yeah, so chlorate is ClO3 with a -1 charge. If you cross it down, plumbic chlorate looks like this, PbClO3 4. But that's harder to work with, right? If we want to assign oxidation numbers, we want to split it back up into its cation and its anion, which is what we had on the left here. So that already tells us what the oxidation number for lead is. It's +4, right? And the oxidation number for oxygen, let's use our little algebra again to solve this, okay? So we know we have how many oxygens?
3
3 oxygens, and each one has a charge, an oxidation number of what?
-2.
-2. And we have how many chlorines? One chlorine, do we agree with that? Yeah, 1 chlorine. We're gonna say X. And this is equal to the overall charge of the chlorate anion, which is what?
-1.
-1. All right, so when we multiply this out, we get x minus 6 equals -1. Because -2 times 3 is -6, right? And to cancel this out, we add 6 to both sides. And we get x is equal to 5. So that x is telling us the oxidation number on the CL. So +5 here. The oxygen has a -2, and then the lead is, it already tells us it's +4, right? All right, any questions on that? How do y'all feel about
Fine.
that? Do you think you understand it a little better? All right, so on these problems, when you have time, try them yourself. And you can, even maybe after this session, you can let me know if you want me to check your answers, okay?
Okay, thank you.
You're welcome. Rich, you wanted to do these? No. All right, Rich is gonna go do number 2. You guys, looking like Shreya's out here.
All right, anyways. So iron, right, what's his oxidation state, do you all think? 0, right, why is it 0?
Natural form.
Yeah, it's in its elemental form, its natural form, so it's 0. What about sulfur? Also 0, right? And then if we look at FES, what's gonna be our total, or sorry, our, what's it called? What's gonna be the oxidation state of iron and sulfur? Or not together, but like separate.
Oh,
Okay, iron separate, sulfur separate.
+2.
+2 for what? The iron or the sulfur?
The iron, and then the sulfur is -2.
Yeah, right, because sulfur follows the same rules as oxygen, has similar chemical properties in that. So it'll be -2, and then the total charge equals 0, then the iron also equals 2. So looking at these oxidation numbers, right, is this a redox reaction or not a redox reaction? Redox reaction, exactly, because your oxidation state of iron changed from 0 to +2, meaning it was what, oxidized or reduced?
Oxidized.
Oxidized, yeah, because it's losing electrons.
Right out there.
Yeah, so there's two ways of going about it. There's either oil rig,
It's only
so
one way, it's oil rig.
oxidation is lost and reduction is gained. But the way I learned it is this, Leo the lion knows dirt.
Nobody does that.
Losing electrons is oxidation, gaining electrons is reduction.
Yeah.
Let me check that. It's oil.
Oil rig makes more sense.
No,
Oxidation, it loses, reduction, it gains.
yeah, but losing electrons is oxidation, gaining is reduction, active and passive was.
That's why he's the English.
Question.
Yeah,
So the thing that's being oxidized is the reducing agent.
yeah, the
Right.
thing that's being oxidized is a reducing agent.
Okay.
The thing that's being
Yeah.
reduced is the oxidized.
Because in order to be oxidized, something has to be reduced.
Reduced.
So if you're being oxidized, then you're reducing something else.
Okay.
So the agent, you're the agent that's doing the reducing by getting oxidized,
Okay.
if that makes sense.
Yeah.
No, sorry, can I say that again?
Yeah, so for oxidizing agents and reducing agents, it's kind of flip-flop. So the thing that's being oxidized is actually the reducing agent, because in order to get oxidized, you have to lose electrons, right? And in doing so, you're giving your electrons to something else, so you're reducing something else. So you are the agent that is reducing something else. Does that make sense? Yes, so if you forget, they're always flip-flop. So oxidized is the reducing agent, reduced is the oxidized agent. Yeah. This, okay.
How's Jen Kevin? Is there an OChem recitation today?
I thought there was,
I'd be on Zoom. I don't know.
maybe.
All right, so BR2, right? What's the oxidation state? You don't think?
Zero.
Zero, right, because it's in its natural form. Bromine's one of those diatomic elements. What about iodine and potassium iodide?
Um,
Plus one, that's one.
Yeah.
So plus
Be
one.
-2.
Plus one and minus one. And then what about the bromine in the products?
Again, minus one for bromine,
Yep, and then what about the iodine?
wouldn't that be zero?
That's zero, yeah. So is this redox or not redox?
You check, when you say that you check all the products,
Wait, sorry, can you repeat that again?
so when you're looking for the redox or no redox reactions, you only see the product, no the reaction of which size.
I mean, you look at both sides, right? So like bromine, see how it went from zero here to in the reactants to -1 in the products? So you look at both sides. So like to see, I get the number change from the reactants to the products. That's how you know it's a redox reaction. So in this case, 0 to -1, right, is bromine being reduced or oxidized? Exactly. Now what about iodine? Is it being reduced or oxidized?
Oxidized?
Exactly. So this is a whole redox reaction. Whenever I see, right, like elements, like elemental states, like if it's in a compound like CnCl2, then it goes to like Zn solid. That's my key to say that this is a redox reaction. There's always going to be like zinc is your +2 here, right? Like oxidation state, it's going to be 0 over here. So it's obviously there's obviously something going on with the oxidation states.
So you would say something like a general rule, single displacement reactions are always redox reactions.
Generally, yes, but it is important to check your oxidation states to make sure you don't screw up come test time.
Is there a way any of y'all, like, some of the key atoms such as red? We'll probably post the video and then obviously you can run through the video. If we finish, yeah, we'll post the key, okay?
I have a question.
Yeah.
So you'd say that the bromine is being reduced, but would you say that the potassium iodide is being oxidized or just the iodine?
Just the iodide.
The iodine, okay.
Where you use the entire reactant is if you're talking about oxidizing reducing agent.
Okay.
So since the iodine is being oxidized in this case, it's the reducing agent because it contains the thing that's being oxidized. Like reducing agents, like the thing that helps the other thing get reduced.
Yeah, so the agents are always the reactants. They're never gonna be a product, okay? And yeah, so your agents are gonna be the entire compound. What's being oxidized is the specific atom in the thing, or what's being reduced is the specific atom in the compound, okay?
So you'd say BR, not PR2?
Yeah, bromine is being reduced.
Okay.
Fine. Now, BR2, if it's being reduced, then BR2 is the oxidizing agent. You can't say bromine is the oxidation, BR is the oxidizing agent.
So any questions on that before we move on? All right, let's go to this next one. Heptane plus O2 makes carbon dioxide 1. So remember, right, your hydrogen is always +1. So if hydrogen is always +1, what's going to be your oxidation state on carbon? Yep, -2, because the entire thing has to add up to 0. So O2, right, what's going to be your oxidation state of that? 0, right, because it's elemental form. Now, if we look at CO2, what are the oxidation states of both those elements? -2 for the oxygen, right? But you're close on the carbon. Remember, right? It adds up to 0. So -2 times 2, and then the carbon X. So X equals 0. So then you'd say X minus 4 equals 0. Now to solve for X, right? You would add both sides by 4. Then you get X is plus. Then your water, right? It's -2 for oxygen, and then +1.
Balance it first. He's asking if we have to balance it first.
Oh, you don't, I was just stating that that was unbalanced, just so y'all don't get confused.
Yeah, oxidation, whether it's balanced or not, oxidation numbers should not change. Because whether you have one molecule of heptane or two molecules of heptane, you would expect the oxidation number of each atom in heptane to be the same, right? Okay, perfect.
So seeing that the numbers change, right, is this a redox reaction or not a redox? Redox, yeah, because the numbers change. What's being oxidized and what's being reduced? Carbon's oxidized, right? Exactly.
And what would you say about combustion reactions in general?
I'd say that in general, combustion reactions are generally redox reactions, but also, again, check your oxidation numbers, because that's not always the case.
Well, I would say because oxygen is always in its elemental form on the left, and it's always going to be in an oxide on the right. It's combustion reactions are always going to be redox reactions, and every combustion reaction, oxygen is being reduced, right? And every combustion reaction, O2 is always the oxidizing agent, right? So that's just things you should kind of, I wouldn't say memorize, but just know, like, oxygen is always going to be reduced in a combustion reaction.
Here the reduce, the one that it's reduced, it's which
It's the oxidizing agent. Because in order to be reduced, something else has to be oxidized. Because the electrons have to come from somewhere else. So if it's gaining electrons, if you hand me a handful of electrons, I'm gaining the electrons, you're losing it, right? I'm being reduced, you're being oxidized. But I'm the oxidizing agent, because I'm saying, hey, give me your electrons. You're the reducing agent because you're the one handing me your electrons.
so here it's
If oxygen is reduced, then that means something is being oxidized, right? So oxygen is the oxidizing agent. It's kind of, I had a little bit of a hard time when I first was introduced to this, because you're like, wait, it's being reduced, but it's the oxidizing agent. That doesn't make sense. But once you start thinking about it in the sense that if it's being reduced, then something else is being oxidized, right? So if it's being reduced, it has to be the oxidizing agent, because it's facilitating the oxidation of something else. So that way it can be reduced. Does that make sense?
Yeah, so that is that. Right, so then we'll move on to part D, sulfuric acid and then rubidium hydroxide. So first of all, what type of reaction is this? Acid base, right? So let's see if it's redox or not. So what's the oxidation number of this this oxygen right here? -2, right? Because oxygen is more likely than not -2. Now, what about your hydrogen? What's that gonna be? +1, exactly. So you have your -2, your +1, and then you know that everything has to add up to 0. So -8 +2, because 2 came from here and 4 came from here. So -8 +2 is -6. So then you'll have x -6, and then the entire thing has to add up to 0. So your sulfur is gonna be a +6. So +6 right here. What about rubidium? What's your oxidation number on that? +1, yeah, because it's an alkali metal and that always goes to its charge. What about for hydroxide? So OH minus. Yeah, -2 for your oxygen, because your oxygen always has to be -2. And then your hydrogen, right, is usually +1. So -2 +1 makes your -1. So -2 here, +1 here. All right, so what about oxygen and water? What's that oxidation number? Yeah, +1, because again, it follows your same rules. So oxygen's -2, then your hydrogen is +1. All right, moment of truth, rubidium. What's the oxidation number on that? Yes, it's still the same, +1. So now what about your sulfur? Or or I should say the entire like sulfate. So let's break it down. SO4 2 minus. What's the oxidation number for oxygen? -2 exactly. And so you have -8, and you need to get to -2. So what do you add?
6.
+6, yeah. So +6 on your sulfur, and then -2. So knowing this information, is it a redox reaction? It's not, right? Because nothing changes. So not redox.
And a general rule is that acid-base reactions are the transfer of protons. And that transfer of protons does not involve the transfer of electrons. In these acid-base reactions, when you have a proton being transferred to the base, right? Your acid's donating a proton to the base. So therefore, these acid-base reactions are not redox reactions. So that's a general rule. Now, there are some different types of acid-base reactions you get into in later classes that could be redox reactions. But when you have an acid like sulfuric acid and a strong base like rubidium hydroxide, you have the proton coming from the sulfuric acid to the hydroxide of the base, right? That's just the transfer of protons. Those acid-base reactions are not redox reactions ever. It's just something to keep in mind, maybe. Okay.
Yep, so that is not redox. All right, what about E? What type of reaction is this? Combination synthesis, yeah, same thing. I like synthesis better, so I'm like, right, yeah. Synthesis. All right, so what is your oxidation number for oxygen and calcium oxide?
+2 for calcium, -2 for oxygen.
Yeah, so it's +2 here, -2 here. What about for water?
+1 for hydrogen, -2 for oxygen.
+1 here and -2, exactly. All right, here's a difficult one. What about calcium hydroxide?
There's +1 for hydrogen. -2 for oxygen.
Calcium is, yeah, you're +2.
Yeah.
So yeah, everything has been decided now, like all your numbers are there. Is it redox or not redox? Yeah, because nothing changes. If you determine that a reaction is redox and only one thing changes, then you've done something wrong.
Yeah.
Because in order for it to be redox, two things have to change. One thing has to be oxidized, another thing has to be reduced, always.
Yeah.
So yeah, this is.
Now, how would you be able to determine F? To say if it's redox or not redox without going through the whole oxidation?
Isn't it because lithium is in its natural state, and then zinc on the other side is its natural state. So they had to have oxidation stay at 0, 1, which means one of them was probably oxidizing and the other one was probably reducing.
Yep, exactly. The bridges are flowing today. It's a redox reaction. Now, can y'all determine which thing is oxidized and which one's reduced?
So isn't it that lithium is being oxidized and zinc is being reduced?
Exactly. So lithium, right, goes from 0 to +1. So that's oxidized, it's losing an electron. And zinc is going from your +2 to 0, so it's gaining electrons. So zinc is reduced. And yeah, that's pretty much it. So whenever you see like reactions like this that have like elemental like metals and then they're in a compound before, that's redox. Oh yeah, now I remember what I was going to say. What is your oxidizing agent in this case?
Zinc chloride.
Zinc chloride, yeah, because zinc chloride is the thing that was reduced. Like, think of it like the thing that's like, if you already know what's oxidized, the reducing or the oxidizing agent's the other one. Yeah. And like, if you know what's reduced, the reducing agent's the other one. It's really obvious. All right, so go ahead and do this. Yeah, we'll go ahead and do G, then we can do some more problems. so what is your oxidation state in calcium carbonate?
Is it +2 for calcium, +4 for carbon, and -2 for oxygen?
+4, let's see, -4, see, -6, +4, -2, +2. Yep, that works out. And then for calcium oxide, right, oxygen's your -2, calcium's your +2. And then what about for carbon dioxide?
+4 for carbon, -2 for oxygen.
Pretty much. So is this a redox reaction?
No?
Yeah, no, right, because there's no, what's called changes in oxidation state. And y'all can do H and I on your own, but we'll try to get through some more problems.
I have a question. So for every time we have like this, the first step is to put the oxidation number.
Yeah, like whenever you're determining if like your reaction is redox or not, it's always like assign the oxidation numbers first. And then check like whether you see a change in your oxidation. Like if something's changing, then it's a redox reaction, otherwise it isn't. Does that make sense?
But I think for me, like to know to get the oxidation number is gonna be like.
Yeah, you would have to do the math for it, you know? So like for calcium carbonate, I would do the reverse crisscross, and we know calcium is always +2 because it's group 2, right? Therefore, and we know carbonate is always -2, has a -2 charge. We memorize that. So if you do the math that we did earlier, you get -2 times 3 for there's 3 oxygens. Plus the 1 carbon is equal to -2, the overall charge. Right? And then when you do the math, you get that carbon has a +4, and we already knew oxygen has a -2.
Thank you.
Yeah, so as I said, y'all can do H and I on your own and check with us probably in like next session or email us like after work and we'll check it over. All right, so go ahead and do question 3.
All right. So a Gen Chem 1 student is tasked with performing a titration with 150 milliliters of a 15 molar phosphoric acid. The student is given a 10 molar solution of sodium hydroxide. What volume of sodium hydroxide solution is required to neutralize the acidic solution? All right, that's a lot of information to process in a single question, right? So it's asking us how many liters or what volume of the sodium hydroxide solution is going to be required to neutralize all of the protons or in the acidic solution, okay? So first, if we want to figure out how much of something is required to neutralize each proton, we should figure out how many protons there are in that solution, right? Does that make sense? We need to know how many hydroxides we need or that we should have in order to figure out how many, I'm sorry, I said that. We need to know how many protons we have and how many hydroxides we're going to need to neutralize each one, okay? Because the neutralizing is just another term for an acid-base reaction when you form water and salt, okay? So to start, let's figure out how many hydrogen protons we have in the acid solution. And the way I'm going to do that is using our molarity equation. So molarity is equal to moles over liters, all right? And we see that we have the molarity and we have the liters. So let's plug in for that. Or let me solve for moles first. I'm going to multiply both sides by liters to get molarity times liters equals moles. In this case, if we plug in what we have, we see the molarity was 15. The liters, it gives us it in milliliters, but we need to convert that to liters. So 150 milliliters is equal to 0.15 liters. So 15 molar times 0.15 liters is equal to 0.15.
You like 2.25?
Yeah, it's actually 2.2499999.
That's crazy.
And that's moles of what?
So page 3PO.
Moles of H3PO4. And if we recognize, let me copy and paste that over here. We can use the ratios to get to how many moles of the H plus we have, which is our proton.
I'd like to add, right, like, y'all might remember H3PO4 is a weak acid. So normally you shouldn't be doing this, like, when you take Gen Chem 2, you learn like, this never happens.
Let's not confuse them for this class, okay?
So just assume all the protons.
Because that's what happens in Gen Chem 1, okay? Okay, so for every 1 mole of phosphoric acid, let's start that. How many hydrogen protons are there? So for every 1 of these, how many hydrogen protons are there? If this acid donates all of its protons? 3, right? Because if we look in this formula, there's 3 H's for each phosphoric acid, right? Does that make sense? Yeah. Okay. So there's 3 moles of H plus. Okay, good. That'll tell us how many moles of H plus there are, and that's what we need to know to figure out the rest of the problem. So times 3 gives us 6.75 moles of H plus. And we know that for every H plus, we need 1 hydroxide, right? Because if you do the reaction, OH minus yields 1 water, okay? So for every H, we need 1 OH, okay? Does that make sense? Yeah,
What about like, I know like Alex is like monoprotic,
yeah,
like,
monoprotic acids
and
and
then
diprotic acids.
yeah, would that be like in the question or? Or I don't, cause
mean, sometimes yes, sometimes no, like,
if it's not there, we just assume it's a 1-to-1 ratio.
or not really, right? Because you write out the formula, like say nitric acid, right? That only has 1 hydrogen, so it's monoprotic.
Okay.
Yeah, that's how you look at it.
Yeah, so yeah, like you said, something like nitric acid has 1 proton to donate, 1 H plus to donate, therefore it's monoprotic, it has 1 proton. Something like sulfuric acid has 2 protons, therefore it's diprotic, it's gonna donate 2 protons, right? And like we see here in this problem,
So what would H3PO4 be?
Triprotic.
triprotic, right? Okay. Let's go ahead and go on with this problem. I'm gonna erase this down here. So if we know that for every mole of H plus, we need 1 mole of OH minus of hydroxide, then we can say that the moles must equal each other. So 6.75 moles of H plus must equal 6.75 moles of OH minus to completely neutralize, right? That makes sense, right? And from there, if we have our moles of OH minus, and since sodium hydroxide is in a 1-to-1 ratio with sodium with hydroxide to compound, or let me try to explain that a little better. For every sodium hydroxide, there's 1 OH minus, right? Right? So it's a 1-to-1 ratio. So for every mole of hydroxide, we have 1 mole of sodium hydroxide, right? Okay. So we want to figure out the liters required of the sodium hydroxide solution. We have all the information we need, right? So based on this fact here, we can say that this is equal to the amount of sodium hydroxide we have in solution, okay? Divided by our liters will give us our molarity. Any questions so far? This is kind of a tedious problem, so go ahead and ask a question if you have the question.
Again, chapter 4, this is probably like the hardest problem I'll see, like concerning chapter 4 topics.
Yeah. so any questions? Can I clarify anything?
You always have to do that like in between of going from the H plus, 6.75 moles of H plus, and then 6.75 moles of.
You don't have to, but because I'm trying to show everyone and explain it, I do it so that way they see that. If you know that, hey, if I have 6.75 moles of H plus and you know in your head that I need to have the exact same amount of OH minus, you can go straight to the next step. But I'm only doing it to try to explain why and where I'm getting this from.
Yeah, if you know that whole relationship, like the H plus equals the OH minus, you can just plug that number in your calculator and then be done.
So we're gonna say this is equal to. I'm gonna backtrack a little bit. So 6.75 moles of OH minus, since it's a 1-to-1 ratio, that tells us that there's 6.75 moles of sodium hydroxide. Okay, right? Because for every 1 sodium hydroxide, we have 1 OH minus, right? So let me backtrack here. Because the answer wants us in sodium hydroxide. All right, so the molarity of the sodium hydroxide solution was given to us, and it tells us that it's 10 molar. 10 molar. And the moles we figured out was 6.75 moles of NaOH. And that's from this relationship here, right? So for every 1 mole of H plus, you need 1 mole of OH minus to neutralize it. And for every 1 mole of OH minus, you have 1 mole of sodium hydroxide. Okay. That's the relationship on why we got that. And divided by the liters, which is what we're solving for. So if you multiply both sides by liters, divide both sides by 10 molar, you'll get liters is equal to 6.75 moles NaOH over 10 molar, which just gives you, let me bring it up. 0.675 liters. That's the answer. That's a very tedious problem. We are recording this session. So if you didn't get it this time around, erase all your work, try it by yourself, rewatch the video. And if you still don't get it, erase all your work, try it again, watch the video, and hopefully by that 3rd time, you kind of understand the flow of why I'm doing what I did to get to where the answer that we wanted to, okay?
And if you still don't get it, you can erase your work, rewatch the video.
Basically, okay. You have enough time for one more question. Wow, I'm good. I'm glad we didn't put more questions on this worksheet.
Oh, yeah, definitely.
At the end, if we, Sam, can I ask you a question?
Sure, yeah. In fact, you could even ask it now, because I'm sure someone else has the same exact question on.
No, I think no, because mine is like too obvious.
Oh, okay, well,
I don't want them to, like,
okay,
how do you say, not to learn that.
I understand. At the end, you can ask us, if you feel more comfortable.
All right, so this will probably be the last question for today. A new element, triconium, TK, was discovered. It has properties similar to the alkali metals. Write a double displacement reaction between triconium nitrate and cupric chloride. So how would y'all go about approaching this problem? Any tips, any suggestions?
You need to put first your
Yeah,
balance, and then
Well, that's the answer.
yeah, that's pretty much what you do, yeah. So
Yeah, you could replace,
TK with the group 1 element, exactly, because what triconium is, who knows and who cares? I don't, so I'll just cross it out. It says has properties similar to alkali metals. Unknown alkali metal, let's say lithium. So we'll replace this triconium thing with lithium. Y'all notice like Dr. Armand does this to like confuse you pretty much.
yeah,
Like I gotta think like he had like Obama or like Kardashian, yeah.
if I don't even understand the real ones, I
Yeah.
the fake ones don't help, right?
Yeah, but if he gives you a fake one, it would say like it's similar to this, so just replace it.
Exactly.
So like in this case, now it's like lithium nitrate and then cupric chloride. You all know how to do that. So what's the formula for lithium nitrate?
LiN3.
LiNO3, exactly.
Now, this problem does require you to know what an alkali metal is. An alkali metal is your group 1 elements, right?
Yeah, so that's like your lithium, sodium, potassium, rubidium, cesium, and francium. That's
So,
it.
yeah.
All right, then cupric chloride. Cupric, right, is a higher charge of copper. So what is the higher charge? Like what's the number? Yes, +2. And then chloride, right, -1. Your crisscross method, whatever you call it. I call it loop-de-loop, but CuCO2.
This guy.
Yeah, so CuCO2. And then, right, what will be the products if it's a double displacement reaction?
Oh, do your solubility, like states of matter.
States of matter, right? Right, and lithium nitrate, of course, that'll be aqueous, because like lithium soluble, group 1, nitrate always soluble, so you got that double soluble, that very soluble. Then you have copper chloride. So this is what?
What is copper chloride? Soluble or insoluble?
Isn't it soluble? Because
It's copper 2.
Copper 2. So therefore it is.
soluble?
Say, are you asking?
No, I think it's solid.
It is soluble.
Oh.
Wait,
But are you asking or telling us?
Telling?
You're telling us, right? Because you're confident, you know that it's soluble.
Yeah, we have a saying, if you want to say it with chest.
Oh, it's for sure soluble.
wait, soluble?
Because plus
Yes,
1 is
soluble.
soluble.
Oh, yeah, +1, copper +1 makes halides insoluble.
Okay.
Yeah, it's only copper 1, not copper 2.
Yes.
All right, so now that we have our physical states or whatever.
Soluble because it's a reactant, so all reactants have to be aqueous solutions.
Not necessarily. Sometimes if you have like a aqueous and then a solid, you're gonna get no reaction occurs. So you have to be able to recognize that.
Yeah, so lithium nitrate, right? So what'll be your products now? You do like the flipping of the cation on the anion. So
Yeah. So
lithium chloride, right? And then
copper.
copper, CuNO3. And then, right, since the question's like technically not lithium, it's trichonium or whatever elements that are created, so you'll just you'll replace your lithium for TK. once again. If this is a free response, if it's a multiple choice, like you just recognize TK and then just be on your way. So CuNO3, 2. All right, so this is aqueous and this is aqueous like we discussed. What about this element, lithium chloride? Is it aqueous, solid? What do we think? Solid.
I think aqueous.
Aqueous, exactly. Because lithium is your group 1 and then chloride, right, is soluble. So yeah, it's aqueous. Now, what about copper 2 nitrate?
Aqueous.
Aqueous, exactly, because nitrates are always soluble. So yeah, everything's aqueous here. So that's your double displacement reaction.
Now, would you say a reaction occurred here?
No.
I mean, it's hard to tell.
So when they're all aqueous. does it-
When they're all aqueous, normally doesn't.
What does the net ionic equation look like?
That ionic equation would look like a bunch of canceling out. With respect to
Exactly.
your ions.
Therefore, no reaction occurs in this case. If you were to write out your net ionic equation. Okay,
Right, so we are approaching the end here. It's like a minute left. Should be a QR code at the bottom.
please scan this, and just so for attendance. I've noticed a lot of people just don't scan it and it helps us track data. So on the next exam, we can see if the people that consistently came to our sessions did well. And in fact, I'm not done with all the data yet, but as of right now, the average for Dr. Armand's class on the exam 1 was a 59, right? And the average for the people that came to me and Rich's sessions at least 5 times was a 83. And I'm not done collecting all the data yet, but that, is kind of nice to see for us and to encourage y'all to keep coming to our sessions and to tell your friends to keep coming. Okay, but yeah, so please do this attendance thing. It's not a long thing. But yeah. Thank y'all. I appreciate y'all coming. We always enjoy having people here. And if there's any questions, please feel free to unmute, stick it in the chat. Or yeah.
Yeah, so other than that, Zoom people, if you scan the QR code, y'all are free to go. Have a great rest of your day. And yeah.
Have a good one. Take care. Thank you as well. Of course, Michelle, you have a good day.
So I have three questions.
Yeah.
When it's an iteration,
Mhm.
you always use molarity